Hi dear friends, welcome once again to PDV Lidex Education. So without wasting much time, we are going to continue with our second session of the special tutorial questions, which I said came from a very special source, right? A sacred source. Don't bother, but just make sure that you pay attention to these questions and make sure that you put this video in your favorites, because on that day when you have your GC this academic year, you are going to come back, right, and tell me that, hey sir, who gave you those questions? I've not said much, right? Just put the video in your favorites and make sure that you follow it regularly, and as well as study your books and follow PDV Lidex Education. If you do not know, you can always join us in our various centers in Yaoundé and in Douala, at a Tukebe, in Mendong, or in a source. You can also join us at in Douala, right? The different centers that we do have there. So please, the Lidex does not limit here, right? If you want to do lessons with us personally, then join us in our centers and just write to us. We shall get to you. Okay, so let's dive directly into business. So now we are going to inorganic chemistry. It says that question 2A, what do you understand by the term first ionization energy? What do you understand by the term first ionization energy? So we are going to define two. You know that generally when I'm answering questions, right, I always try to open up so that you can understand better. That's why sometimes I explain a lot, but it's all for your good, and it's also because I also love what I do, and I always want that the students get a better understanding. Yes. So we are asked to define first ionization energy, right? But we are going to do three things. We are going to define ionization energy, then we shall define first ionization energy, and we shall define second ionization energy, and we shall write equations to show them. So what is ionization energy? Simply, ionization energy is the enthalpy change associated with the formation of cations. I believe most of you guys have never heard about this definition. Yes, when they ask you define ionization energy, you shall go ahead and say that it is a heat evolved or it is a heat absorbed when 1 mole of gaseous atom of an element loses 1 mole of electron to form 1 mole of gaseous unipositive ion. What you have defined is not ionization energy, but it is what? It is first ionization energy. Yes. So when they say define ionization energy, right, you are neither defining the first, nor the second, nor the third, but you are giving what? A global definition of ionization energy. And what did I say? Ionization energy is defined as the enthalpy change associated with the formation of cations. The enthalpy change associated with the formation of cations. We call it ionization energy. Now, depending on the charge of the cation, right? Depending on the charge of the cation and from what it has been formed, we have different types of ionization energy. And the first one is called the first ionization energy. So, what is first ionization energy? It is the heat absorbed when 1 mole of gaseous atom of an element loses 1 mole of electron to form 1 mole of gaseous unipositive ion. So let's write an equation. What do we say? First ionization energy is the heat required, right? The energy required to remove 1 mole of electron from 1 mole of gaseous atom of an element to form 1 mole of gaseous unipositive ion. So if I take for example sodium, the heat required or the energy required to remove 1 mole of electron, right? 1 mole of electron from what? From gaseous atom of an element, right? From gaseous atom of an element to form what? To form 1 mole of gaseous unipositive ion. The energy required to remove 1 mole of electron from 1 mole of gaseous atom of an element to form 1 mole of gaseous unipositive ion. We call that one first ionization energy. If I take magnesium, I will have the heat required to remove 1 mole of electron from 1 mole of gaseous atom of magnesium to form 1 mole of gaseous unipositive ion, right? Like that. Now we know that ionization energy is associated typically with metals because metals easily lose electrons. Non-metals don't readily lose electrons. But however, under harsh conditions and with so much energy, we can cause non-metals to lose electrons. So if they ask you, write the equation for the first ionization energy of oxygen, it is not an error. The equation is not an error, it's not a mistake, right? Write the equation. So let's write the equation to show the first ionization energy of oxygen. What do we go? We go by definition. First ionization energy, it is a heat, the energy required to remove 1 mole of electron from what? From 1 mole of gaseous atom of oxygen. Gaseous atom of oxygen, like that, right? To form what? 1 mole of gaseous unipositive ion. That is the equation that shows the first ionization energy of oxygen. It is not a mistake, right? With much energy available, we can also cause oxygen to lose electron. Now, what is second ionization energy? It is the energy required to remove 1 mole of electron from 1 mole of gaseous unipositive ion of an element, right, to form 1 mole of gaseous dipositive ion. Second ionization energy is the energy required to remove 1 mole of electron from 1 mole of gaseous unipositive ion of an element to form 1 mole of gaseous dipositive ion. Let's write the equation to show that. Let's take sodium. Second ionization energy of sodium means that what? We are starting from this. So the energy required to remove 1 mole of electron from what? From 1 mole of gaseous unipositive ion of sodium. So 1 mole of gaseous unipositive ion will do what? It will lose 1 mole of electron to form what? To form 1 mole of gaseous dipositive ion. This equation shows the second ionization energy of sodium. If I take oxygen, 1 mole of gaseous unipositive ion of oxygen does what? It loses 1 mole of electron to form 1 mole of gaseous dipositive ion. That equation shows the second ionization energy of oxygen. Okay, I hope you have understood the meaning of ionization energy, first and second ionization energies. Next question says ionization energy can be determined using the electron bombardment method, right? Ionization energy can be determined using the electron bombardment method. Roman 1. State the function of the following in the process. 1. The potentiometer. Yes. So here we want to see how to determine ionization energy experimentally, right? The method used is called the electron bombardment method. So how does the method comprise? Right, we have an apparatus like this. Then inside here we have a cathode, right? A cathode that we are going to heat. So here we are going to heat the cathode and we'll hit the cathode. Then at the top here we have our anode. The anode is going to be made negative. The cathode, of course, will be positive. Now here we have a grid system, right? And from the grid system we are going to measure current. Then here we shall also have a potentiometer, right? If a potentiometer that will enable us to measure voltages. Then the potentiometer is going to be used to generate a PZ, right? So this one, we call this one the potentiometer. The potentiometer. Now, this is the electron bombardment method. What is a principle? We are going to ionize, we are going to vaporize a sample, right? We shall vaporize the element for which we want to get the ionization energy. We vaporize it and introduce it into this cathode anode chamber. So the cathode is going to be heated and it will produce electrons. It will produce a stream of fast moving electrons. The electrons are going to migrate towards the anode, and since the anode is negative, the electrons will be repelled. They will be repelled and sent back into the anode cathode system. Right? This is a grid. The grid is used to serve as a passageway for current to be measured in the circuit using an ammeter or a milliammeter. So we are asked to give the function of the following. 1. The potentiometer. The role of the potentiometer is to generate to increase the PZ required to accelerate these electrons, because the vaporized sample is introduced here, and the goal is that the cathode will be heated. It will produce electrons, and those electrons are going to knock off electrons from the vaporized sample. So for example, if sodium is my vaporized sample, right, what will happen? This is my vaporized sample, sodium gas. The cathode will produce electron, and that electron, that special electron, is going to do what? It will knock off electron from the shell of sodium, and sodium will lose electron, right? Sodium will lose electron plus the special electron. So then what happens? This electron is from the cathode. It knocks off electron from sodium, causing sodium to become what? Ionized. And from there we can get the ionization energy. So the function of the potentiometer is to increase the PZ required to accelerate the electrons produced from the cathode, ensuring that they can readily knock off electrons from what? The vaporized sample. Right? The potentiometer's role is to increase the PZ between the cathode and the anode so as to accelerate the electrons and facilitate the ionization process of the vaporized sample. Now the next thing, we are asked to give the function of the cathode anode circuit. This is a cathode anode circuit. This circuit is a cathode anode circuit. What is its function? Its function is to generate and maintain the electrons required to ionize the vaporized sample. Right? The function of this circuit is to produce, the cathode produces the electrons after being heated, thermionic effect. The anode repels the electrons, ensuring that they go and knock off the vaporized sample and cause it to ionize. So in summary, the function of the cathode anode circuit is to produce and maintain the fast moving electrons required to knock off or required to ionize or to cause the ionization of the vaporized sample. The next question says that we should give the function of the cathode grid circuit. Right? This is a grid. Right? The cathode grid circuit. The cathode grid circuit. So the role of this cathode grid circuit is to serve as a passageway for current produced to be measured. Right? So any current that is produced in this circuit is going to flow through the grid and will be measured by the ammeter. So the cathode grid circuit serves as provides the pathway for current to flow in the circuit, right? So those are the functions of the three major parts of this apparatus that measures ionization energy by electron bombardment method. Now the next question says that the ionization potential for an element X was found to be 8.6 volts. What is the ionization energy of this element? They tell us that the ionization potential V, right, of an element was found to be 8.6 volt. What is the ionization energy of the element, right? Okay, so as we know, ionization energy, right, is given as the charge times the potential times the Avogadro constant, right? The charge times the potential will give us the energy in total. But now when we multiply by the Avogadro constant, we now have the energy per mole, kilojoule per mole, right? So this is the formula that we shall use to find the ionization energy of the element. So what do we have? The charge here is a charge that is being removed from the element, and that charge is what? An electron, right? When the element is ionized, it has a charge of plus E, which is a proton. So the charge here is 1.6 times 10 to the minus 19, right? Because when the element is ionized, this is what it forms, right? The overall charge here is an excess proton, and a proton is plus 1.6 10 to the minus 19 coulomb, right? So that's a charge. Now, the potential is 8.6 volts, right? Volts. Then the Avogadro constant is, this is the formula. The Avogadro constant is what? Is 6.02 times 10 to the 23, right? This one is in coulomb. This one here is in volts, and this one here is in per mole, right? Avogadro constant has units of what? Per mole. So when you punch that, you are going to have 828.352, right? Volt and coulomb will give joule, and then you have joule per mole. But as we know, this energy of ionization is always given in kilojoule per mole. So we could write it in kilojoule. Alright, please, this is not point, this is 1,000. So it will make positive 828.4 kilojoule per mole. So that is the ionization energy of the element. Now the next question says that, very fast, the next question, it says that the hydrogen emission spectrum shows different series of lines known as Lyman, Balmer, fast chain, and series. It says that the hydrogen emission spectrum shows different series of lines known as the Lyman, the Balmer, the fast chain, etc. series. First question, why are there several lines in each series? Why are there several lines in each series? Okay, here we are going to demystify the hydrogen emission spectrum. So let's draw a diagram to show the hydrogen emission spectrum, right? Here we have the continuum, right? The continuum. Then as we go down, that is how the energy levels are increasing. So until we have the lowest state. The lowest state is called the ground state, right? The ground state. And the quantum number there is n equals to 1. Here we have n equals to 2, n equals to 3, n equals to 4, up to n equals to infinity, n equals to 5, and so on. So the ground state is a state that is closest to the nucleus, right? It has the lowest energy. The nucleus is just around here. So the lowest energy level closest to the nucleus is called the ground state. As you go up away from the nucleus, the energy increases in electron volt or in joule. So electrons in the hydrogen atom can occupy discrete energy levels. These energy levels show that the energy value of electrons in the hydrogen atom is quantized. That means that electrons can only have specific discrete energy values, right? The existence of energy levels show that the energy of electrons in orbit are quantized. So these are the different energy levels an electron can occupy. When electron transition from high level to the ground state, from high level to the ground state, right? Any high level to the ground state, any high level to the ground state, any one. This series of lines are called the Lyman series. So this is Lyman series, right? Lyman series. Lyman series represent transitions to the ground state. Transitions from any higher energy level back to the ground state is called a Lyman series. And the radiation emitted here, they fall where? They fall in the ultraviolet spectrum, right? They fall in the ultraviolet region of the electromagnetic spectrum. Now, when the electron transition from a high state to the first excited state, or to the energy level n equals to 2, right? The ground state is unique. All other energy levels apart from the ground state, they are generally called excited states. So we call this one excited states, right? They are excited states. So when electron transition from any excited state to the ground state, that series of lines produced is called a Lyman series, right? And the radiation emitted there falls in the ultraviolet region of the electromagnetic spectrum. Now, when they transition from higher energy levels to the first, the one here is a first excited state, second excited state, and third excited state, and so on. So when electron transition from higher energy levels to the second energy level, or the first excited state, with quantum number n equals to 2, we call that one the Balmer series. This is the Balmer series. The Balmer series transitions to what? To n equals to 2. And the radiation emitted here fall in the what? They fall in the visible region, right? The visible light region, VL for visible light, of the electromagnetic spectrum. Now, when electron transition from high state to what? To the second excited state, or the energy level n equals to 3, right? We call that one, the series of lines produced there are called the Paschen series. The Paschen series. So Paschen is what? Transition from high level to what? To n equals to 3, or to the second excited state. And the radiation emitted there fall in the infrared region. The infrared region of the electromagnetic spectrum. Now, after Paschen series, we have the bracket series and the Fon series, right? The bracket is transition to n equals to 4. The Fon is transition to n equals to 5. And the bracket, the Fon, and the Paschen series, they all fall in the infrared region of the electromagnetic spectrum. So this is the hydrogen emission spectrum. Now, what we said? We said that the hydrogen emission spectrum consists of what? Different series of lines. This one is a Lyman, the Balmer, the Paschen, and so on. The first question that will ask you here is that, what does each series of lines represent? Well, whenever this question comes in the GC, the first thing they'll ask you is that, what does each of these series represent? What do these series represent? The answer is that the series represent electronic transitions from higher energy levels to lower energy levels. What did I say? The series of lines in the hydrogen emission spectrum represent what? They represent electronic transitions from higher energy level to what? To lower energy level. If they ask you, what does the Lyman series represent? The Lyman series represent electronic transitions from higher energy level to what? To the ground state. What does the Balmer series represent? The Balmer series represents electronic transitions from higher energy level to what? To the energy level n equals to 2, or to the first excited state. What does the Paschen series represent? It represents electronic transitions from higher energy levels to the second excited state, or the energy level n equals to 3. Right? So, what do the series of lines represent? In general, the series of lines represents electronic transitions from higher energy level to lower energy levels. Next question is that, Why are there several lines in each series, right? Why are there many lines in the Lyman? Why are there many lines in the Balmer? Why are there many lines in the pass chain? As simple. The reason, right? Bon, the reason why there are many lines is that electrons in atoms have discrete energy values, and as a result, they can undergo a various number of transitions. What did I say? The fact that there are many lines in each series justify or tell us that electrons in atoms, right, or the electron in the hydrogen atom has specific energy values it can acquire, or has discrete or specific and discrete energy levels it can occupy, from which it will carry out different transitions in the same series, right? So let's answer properly. Why are there many lines in each series? There are many lines in each series because electrons in the electron in the hydrogen atom has specific and discrete energy values it can have at different energy levels, from which it can undergo various transitions in the same series. Yes. Next question is that how can ionization energy be obtained from the emission spectrum? How can you use this emission spectrum to find the ionization energy of hydrogen? Right? It's very simple. You just have to measure the frequency, right? This infinity here, we call it the continuum, or the continuum, right? Or the convergence limit, right? So to measure ionization energy, we are going to calculate the frequency required to remove an electron from the ground state and send it up to infinity. That frequency required, right? That frequency required to take electron from the ground state to infinity will cause ionization. And from there, if you want to get the energy of ionization, we shall simply take the frequency of ionization, multiply with the Planck constant, right? And then multiply with the Avogadro constant. So the question is that how can ionization energy be obtained from the emission spectrum? The answer is simply by measuring the frequency at the convergence limit or the continuum and multiplying it with the Planck constant as well and the Avogadro constant. Once again, by measuring the frequency at the convergence limit or the continuum and multiplying it with the Planck constant and the Avogadro constant. Okay, let's rapidly run and complete this session. So very fast, let's complete this section. The last question is on radioactivity, right? It's on radioactivity. So it says that radioactivity can be used to find the age of artifacts, right? To find the age of artifacts. How old is an ancient painting with a carbon 14 activity of 7.6 count per minute per gram if the initial decay rate of carbon 14 is 15.3 count per minute per gram and the half-life is 5,730 years? So they've given us the initial count rate or the initial activity. It is 15.3 count per minute per gram, and they've given us the activity after the H, which is what? Which is 7.60 count per minute per gram, right? And they've given us the half-life of carbon 14, 5,730 years. And we are asked to calculate the H, right? The H means the time at which we measure this activity. That's what they call the H. The time that corresponds to this activity is called the H of the ancient specimen. So we use the radioactive decay formula. We have that word AT equals to A naught exponential minus lambda T. Lambda is what? Lambda is ln 2 all over the half-life, right? Ln 2 all over the half-life. So we solve. We are solving for the time. The h is the time. So we divide. We have AT on A naught equals to exponential minus lambda t. We apply logarithm of both sides. Natural logarithm ln AT on A naught equals to, when you apply ln here, it will give you minus lambda t. What is lambda? Lambda is ln 2 on t half. So minus ln 2 all over half-life times the time. We want the time, so we cross multiply. The h, or the time, will be given as what? Minus, we bring it here, minus the half-life divided by ln 2 times ln AT all over A naught, right? We substitute the values. Minus half-life 5,730 years all over ln 2 times ln AT is 7.6, A naught 15.3. When you punch that, it will give you the half-life as 5,784.2 years. That is the half-life of the specimen. Next question. It says that next question. Give two dangers of radioactivity. Give two dangers of radioactivity. First, exposure to radiation. Exposure to radioactivity can cause skin burns. Secondly, prolonged exposure can cause immediate death. If you prolong exposure to radioactivity, you can have immediate death. More again, exposure to radioactivity can cause what? It can cause cancer, right? Cancer of the cardiovascular system or the circulatory system, and so on. So radioactivity can cause what? It can cause skin burn. It can cause immediate death, right? Due to high doses, and it can also cause cancer, right? As well as cataracts, the eye disease. So that brings us to the end of this session, guys. Please like the video, share the video, and tell your friends about PD Validex Education. Follow us on Facebook, on YouTube, and on TikTok. And please share our videos to encourage us in what we are doing to help you. Please promote the educational biome of pure excellence, PD Validex Education. If you have any challenges in upper seed science or in lower seed, join us in our centers in Yaoundé and Douala, or write to us in the comment section and we shall attend to you. God bless you and keep working hard for your examination and your future. Bye bye.